Hello everyone and welcome to another lecture. Today we'll be talking about how we can deal with vector functions in Mathematica. So first we need to know how we can declare a vector function. So let's call it declaring a vector function. So how can we do that? The idea for declaring a vector function, let's say I want to call it v, and let's just say I want the vector function to have x component as x, y component as y, and say z component as z. So the idea is you have to put two curly braces, that is in Mathematica you have to give input as a list. So this is x, y and z, right? Let's run it, and this is just showing this. Now you can see that once you do this, Mathematica will suggest you to take the curl of it, the divergence of it, and let's say I want to evaluate the curl. If I do that, you can see that, okay, so there has been some glitch. It's not showing me whatever, like it is showing some hold. So let's do this manually. Instead of this thing, let's just type curl, and for curl you will need the coordinate system and the function itself. So let's say this is my function, and to give the coordinates I have to type x, y, z. If I do that, as expected, this is 0. Similarly, I can take the divergence of it, just type div, and you take v, and you take x, y and z, and if you run it, this is the divergence. And now let's say I have a scalar function, because if you recall from vector analysis that if you had a scalar function and you take the gradient of it, the end result is a vector itself, that is a vector function. So to do that we have to type grad, and let's say I want to give some scalar function, let's say pq squared, suppose, and plus I say, let's take another variable as s, and we have something like this, a bit complicated. And how can we use grad? As you can see, you have to give the function and then you have to specify the coordinates. So here our coordinates are p, q and s. So if you do that, the result is a vector function, and let's call it, suppose, test. This will be our test function. Run it again so that Mathematica knows it, and now again we want to compute the divergence of test, and this time we're doing in PQR, right? So that's why you have to do this. Instead, if you had typed x, y and z, see what happens. It gives you a 0, because Mathematica doesn't know that whether you're using PQS or XYZ unless you mention them specifically. So this is how we can do the elementary operations for vector functions. You can also add two vectors. Let's say I want to add this test and this v, but it won't work, because that is, it won't give us the desired result, because one is in XYZ and another one is in PQ. Yes, so what we need to do, let's say the instead PQ, let's type y, x, and for instead of s, let's type z, and instead of q we are replacing it with y. So again we are replacing all the stuffs, and let's add them. So let's see what happens. So we want to add test and v. You can see that it has added the component wise thing very successfully, and you can even plot this thing, this test plus v. Let's call it test1, just another name, test1. And since this is it has 3 components, we have to do a 3D plotting. To do that, you just type vector plot 3D. As you can see, there are 2 options, one is vector plot, another one is vector plot 3D, and we go for vector plot 3D. To know how to give the input, it says that you have to give these components in the first list, in the second, third, and the fourth. You have to specify the ranges for x, y, and z. And here we are dealing with only 3 coordinates, so I can just type test. Then I need to type the x ranges, let's say from -2 to 5. I want y and z to be the same, so let's do it. 5. If you do it, you can see that Mathematica will give you a very nice plot, and these are the direction fields with arrows, and you can see some nice features with this plot, because you can see that some of the arrows are bigger, some of them are smaller. So the magnitude of the field test, oops, I didn't use test 1, sorry, there's a bit mistake. Yeah, there's a bit of a mistake. So this is just test 1, so instead type test 1, and as you can see that these bigger arrows, they have larger magnitude, and the smaller arrows, they have less magnitude. And you can even use color it as you want, so you can go for vector scale. You can type, let's say I want to type green. Oops. And you can see that this has turned into green, and instead of that, what if I turned red? So this is how you can choose your color, and you can see that the colors are changed. So this is a very nice way to visualize a vector field. The next thing we're going to see is similar, that is we are familiar with the force law, that is the inverse square law for let's say the Coulomb force or the gravitational force. So we're going to talk about that now. We are going to demonstrate that how we can see those field lines using Mathematica. Now let's talk about some force fields and how we can visualize them in Mathematica. So first I want to write force fields. Let's say you are dealing with a physical system and it gives you a force of the following form, that is on this form. So you can easily use Mathematica to plot it. And let's say I want to plot vector plot, but I have to use 3D because I am in a 3-dimensional space. So then I have to write f, then I specify the ranges of it, x from -3 to 3. Similarly for y, -3 to 3. And for z, I want to have, let's say I want to take another interval, let's say from -5 to 5. If you do that, you can see that all the arrows are pointing inward. So let me enlarge this picture a bit. You see that this is the point where these force fields are directing. That is, it's a 3D plot of an attractive force field, and there is a source at the center, and as you approach this source, these arrows are getting bigger. So that means in the vicinity of the source, the force is very strong, as you would expect from the force law. Let's try to see another plot, but this time we will see a 2-dimensional plot. So let's call another vector function, and I want to call it as sin x. Oops. Okay, my caps was on, so sorry about that. I want to call it as sin x and cosine let's say y. So first you run this. So there is our vector function. The x component is sin x, y component is sin y, and then let's take vector plot. We want to g, and we can do from, let's say, -4 to 4. we take y to be, let's say, -5 to 5. Okay, I missed a comma. So, and as you can see, this is a very nice diagrammatic representation of this vector field, and you can draw some interesting conclusions depending on the problem that you are dealing with. And finally, what I would like to do is that I want to see, I'll take this force law and I'll take another force law, and I want to superimpose them so that I can compare. So let's try to take another force law, let's say small f, and I'll just take this thing, but instead of minuses I'll just get rid of those minuses. So in principle this would mean a repulsive force. So let's get rid of these minuses. And at the same time, in the denominator, I'm gonna raise it to a power of 3/2. So in the denominator, you just type this 3/2, and let me just copy it so that I can paste it easily. And after that, I want to use this vector plot 3D. I want to write f, and I want to take the same interval as this, but it doesn't matter, you can take some more greater interval, but just for comparing I'll just take this interval. So if we do that, this is our vector field, and as you can see, okay, let me choose another color. So vector style, oops, let's call it red. Okay, and as you can see, this force dies down faster as the distance increases. That is x squared plus y squared plus z squared. This thing increases. This dies down much faster than the one we have seen here. And now I want to, what I want to do is that I want to superimpose these two pictures, that is this one and the other one. To do that, again we can use the command called show. So what we will do, we will just use show f comma small f. Okay, so this is not giving me anything because what I did here, because this f was this guy and not the plot. So let's give these plots a name. So let's call it f plot, run it again, and let's call this small f plot. Just run it again, and here you need to type f plot, small f plot, and there you go. So what happened here is that Mathematica just put these two pictures together, and though this is not an ideal way to compare, because you can see these colors are overlapping and all that, but it's a start. So you can see some suggestions that it's calling a remove bounding box. So if you do that, you see that the box is gone. The box that it had is gone, and now there are just these axes, that is x, y and z, and if you just make this axis off, everything is gone, and what you have is just your vector field. So this is how you can visualize these vector fields using Mathematica, and this will be it for today, and I'll see you guys on the next lecture. Thank you.